Hey everybody, Dr. A here, and in this video we're going to be providing some background information on a cross-section property known as moment of inertia. So let's go ahead and get started. Moment of inertia is also called the second area moment, and the reason why is because the way we derive the governing formulas and values for a moment of inertia is generally by taking an area moment about an axis twice. So it's like we're revolving a particular area about a particular axis of the shape two times. Now in a full-blown statics course, you'll probably go through that process. In this video, I'm just giving you a brief overview of some overarching formulas for simple shapes and how to deal with composite shapes. So the next thing we need to keep in mind is that moment of inertia is a cross-section property that's computed about one of the shape's axes. Generally, that's going to be a centroidal axis. So every two-dimensional shape or area is going to have two moment of inertia values that we're mostly going to be interested in. The first one is going to be called I sub x. This is the moment of inertia about the shape's centroidal x-axis. The next one is called I sub y. This is a moment of inertia about the shape's centroidal y-axis. So let's take a look at a shape, for example. I'm going to draw kind of a blob of a shape here, okay? Now this blob could represent any shape. It could be a rectangle, a triangle, a C shape, whatever we want, okay? Now let's say that we have its centroid right here, okay? And so let's call this the centroidal y-axis, and we'll call this the centroidal x-axis, okay? So if these two axes represent the axes going through an origin that is the centroid, so maybe we'll make a note here and call this, x bar comma y bar, then what we're looking at is this property, again, known as moment of inertia, about a particular axis, either Ix being the moment of inertia about the shape's centroidal x-axis, or Iy, okay? Now, there is a third moment of inertia value for the shape. It's called polar moment of inertia, also labeled sometimes as I sub z. So I sub z, we also sometimes use the letter J. This is called the polar moment of inertia. Now, we call it polar moment of inertia because it's a moment of inertia about the centroidal z-axis, and in this figure, the z-axis is, you can think of it as it's coming out of the screen at you. Okay, now again, the focus of this topic is really going to be on Ix and Iy. Iz is similar, but we're, maybe in a different video, we'll explore that a little bit more explicitly. So let's keep rolling. It turns out we can derive formulas for simple shapes pretty easily when we want to calculate a moment of inertia about a centroidal x or y axis. Now here I've drawn a rectangle. So let's start with a very simple rectangular shape. If you have a rectangle that has a base width of b and a height of h, then we know that its centroid is right smack dab in the middle, okay? So what formulas do we have for Ix and Iy? Well, I'm not going to derive them. I'm just going to give them to you in this video. So I sub x, again, it's a cross-section property called moment of inertia about the centroidal x-axis right here. That's going to be equal to bh cubed over 12, okay? So it's the rectangle's base times its height cubed divided by 12. Similarly, I sub y is going to be hb cubed over 12. Now again, these are derivable equations. We can use some principles of calculus if we want as well to derive these equations. I'm not going to do that in this video. Again, I'm just presenting these equations to you. And the one thing we need to emphasize, this is for rectangles specifically. Triangles have different governing equations. Circles have different governing equations. This is specifically Ix and Iy for a given generic rectangle. Okay. Now, what if we have composite shapes? Now, if we recall from our previous videos, what is a composite shape? Well, a composite shape is just a combination of several simple shapes that are attached together, okay? Now, to compute the moment of inertia about one of the centroidal axes, either IX or IY, of a composite shape, we first must know the shape's centroidal axis coordinates. So if you want to calculate IX, you need to know actually Y bar. If you want to calculate IY, you actually need to know X bar. So let me give you our generic form of each of these equations when we want to calculate moment of inertia for a composite shape, okay? Get ready. These are going to be slightly bulky formulas. I'm going to say I sub x equals the summation as little I goes from 1 to n of I sub x sub I plus a sub I d sub y sub I squared. Okay? Now, I'm going to go ahead and write the next equation, I sub y, again for a composite shape. It's going to be a very similar formula. Summation I goes from 1 to n of I sub y sub I plus a sub I d sub x sub I squared. Now, these two formulas at first glance, they look a little intimidating. Let's make sure we know what each of these terms mean. Let's start with n, okay? N is the number of parts of the composite shape. So n is the same value that we saw when we were computing the centroid of a composite shape. So we should be familiar with the idea of what n is so far, okay? What about I sub x sub I? I sub x sub I, which we see here, is the moment, I'm going to abbreviate some stuff, moment of inertia about the centroidal x-axis of part I. So what we're saying here is we need to calculate the moment of inertia about each specific part's own centroidal x-axis. Okay, so for example, if we have like a T shape or a C shape or an L shape, the I sub x sub I values will all come from those individual rectangles that make up that composite shape, okay? So that's I sub x sub I. Now I'm going to go ahead and define I sub y sub I because that's going to be a similar definition. It's the moment of inertia about the centroidal y-axis of part I. Okay, now the next obvious one is probably A sub I. Okay, so I'm just going to write that down very quickly for us. A sub I is the area of part I. We saw that concept before when we were dealing with centroid calculations. Now here's the part that people tend to make mistakes on and get confused about when they're doing these kind of calculations. It's these values d sub y sub I and d sub x sub I. So please maybe pay close attention, write this down, rewind the video and watch it again so you have a good understanding of this. So d sub y sub I is the vertical distance between y bar for the composite shape and y sub I for part I. So let's think about that for a second. D sub y sub I, that's for part I, is the vertical distance. So it's going to be a measurement in like inches or millimeters, for example, between y bar for the composite shape and y sub I for part I. Okay? So what would that look like? For example, I'm going to say e.g., for example, if I have an L shape like this, okay, and let's say that my y bar is right here, okay, and let's say that I separate this L shape into two rectangles. So here's one rectangle and here's the other rectangle. So if I'm looking for D, and let's say I call this part 1 down here. If I'm looking for D sub y1, what I'm actually going to be getting is the vertical distance between this centroidal axes defined by y bar and the centroidal axis y sub 1. Oops, didn't mean to skip there. Y sub 1 for part 1. So this little distance right here is going to be d sub y1, for example. Okay. Now, when we do another video where we have a numerical example, we'll go through this a little bit slower with actual values, but this is the basic definition of it. What about d sub x sub I? Now, d sub x sub I, we use that right here in the IY formula. Okay. D sub x sub I is a similar definition, but it's the horizontal distance between x bar for the composite shape and x sub I for part I. Okay, now here's where you got to be careful. It seems kind of backwards, right? But in general, when you're first learning this, you need to just remember when you're calculating I sub x for a composite shape, that's going to utilize d sub y sub I. In the opposite sense, when you're calculating I sub y for a composite shape, you're going to utilize d sub x sub I. And again, we defined these down here. Okay, so this is the background information for how to compute moment of inertia for rectangle and then for composite shapes. In my videos, for now, I'm just going to focus on rectangles so we can kind of wrap our heads around this a little bit more smoothly, okay? So if you found this video helpful, please hit like and subscribe and be on the lookout for the next video, which will have a numerical example going through this. Thanks for watching.